Okay, how did I become a theoretical neuroscientist? I will tell you a slightly straighter version than the real version. But I always knew I wanted to be a theorist, but I also I was very interested in theoretical physics, but I was also interested in biology, and biology seemed like it had much more of the interesting open questions of our current time. So actually, as an undergraduate, I majored in biology, but I did an equal amount of physics. When it came time to go to grad school, at that time, I applied to physics, biophysics, biology departments, and I was uniformly told by the biologists that biology is an experimental field. If you want to be a theorist, you should be in physics. And so I didn't really find an opening to do theory in biology, and I went to grad school in physics, and that's where I got my basic training. And I did all of a dissertation in physics, but I resisted actually signing on with a particle physicist to do my thesis, and I spun my wheels for a few years trying to figure out what to do. And then I found my way into a problem in neuroscience. I took some graduate courses in neuroscience, and I took one course. I was at Stanford, and Carla Schatz, I don't know if you may have heard of her, and Eric Knudsen were assistant professors then, and they were teaching a course on activity-dependent plasticity, and a graduate course. And I took this course, and every paper we read, it just seemed to me like, from micro-level synaptic learning rules, you would get these macro-level structures that they were seeing. And I remember talking to Carla and saying, it just seems like all of this would emerge from a model, but then remembering what all the biologists had said to me, I said, but, I guess models aren't much use in biology. And Carla said, no, I really think we need models in biology. And, the sun broke out through the clouds. And so, to make a long story short, I decided to move into neuroscience. She didn't do theory, but her friend Mike Stryker, who was an assistant professor at UCSF, liked to play with computational models. She referred me up to him. I started working on a model of ocular dominance column development, and eventually I transferred into the neuroscience program and went and did my PhD with Michael at UCSF, got my PhD in neuroscience, and I did experimental as well as theoretical work, just because I wanted to taste it. I wanted to know what it was about. And when I started my own lab at UCSF some years later, I tried to have both experiment and theory, and that eventually worked out, but my heart was really in the theory. And so when I moved to Columbia in 2004, I left the experimental behind and just did theory from then on. So that's the short version. Okay, I have kind of an ambitious idea of how much I'm going to cover, and we'll see if I really get there. I wrote up here an outline, so if I get totally disorganized, you can try to remember where I am. I'm basically going to briefly introduce rate models, but not really say much about them, but that's the set of models I'll be studying are rate models. I'm going to talk about where selectivity seems to come from in visual cortex, why you're selective for some patterns of input versus others, and then what is the answer is going to be basically that it looks to be largely determined by the feed-forward input, although maybe not entirely. Then the question is, what is all the cortical connectivity doing for you? And of course, this isn't a complete answer, but one thing that it's doing for you is modulating the gain in a dynamic way, depending on context, depending on lots of other sort of globally what's in the scene. And so we're going to talk about how do you modulate gain first linearly. What are the basic mechanisms? Then what seems sort of a diversion, we're going to talk about why do we have irregular firing, which was the motivation for what's called the balance network of Van Rieswick and Sampolinsky. And I'll just very briefly introduce some of the main ideas of that. There's a whole, that could be many lectures. And then I want to talk about work we've been doing recently on what we call the stabilized superlinear network, which kind of knits these together, and that it explains a lot of nonlinear gain modulation in cortex. And it also turns out to be a loosely balanced network. It has a close relationship to the balanced network, but in a different parameter regime where the balance is loose rather than tight. And if I'm lucky, I'll get through all of that, but that we'll see. Okay, so rate models. Yesterday, Tim wrote down an equation that should have ended up something like C over the sum of all your conductances dV by dt is negative V plus the sum of your conductances times the reversal potentials over the sum of the conductances. And he called this E, and he called this tau. But these were both dynamic variables because your conductances are dynamically changing. So does that all look familiar? I don't know if he presented it in exactly that form. And if you now butcher this a little bit, if you assume that we're going to forget about total changes in conductance. You either just assume the conductance is constant or just say we're forgetting about conductance effects. And so we're not going to worry about these denominators. We're just going to call this tau, but it's going to be a static time constant. We're going to forget about this denominator. And this numerator, we're going to imagine the input to the neuron can be written as a set of a matrix of weights times the vector of firing rates. So these weights would be positive. Basically, you work in a voltage system where the reversal potential of excitation is positive and the reversal potential of inhibition is negative. And so you end up with positive weights for excitatory cells and negative weights for inhibitory cells. And we ignore spike times, and we just assume that the weights times the rates give us the conductances, and then plus there's some external inputs from outside the network. Let's just call that H. So R is a vector, H is a vector, V is now a vector.
And we didn't talk about networks, we only talked about single neurons.
Okay, but so if you imagine okay, so for a single neuron, it's the sum of, let's say neuron number I, sorry, let's make it, I already used I, let's make it neuron number K, then the input would be sum over J of WKJ RJ, all the other inputs onto cell number K, times the weights onto K times their firing rates, and then the feed-forward input to cell number K. And so if you do that, and if you also assume that the firing rates are some nonlinear function of the voltages, and we'll leave the nature of that nonlinearity unspecified for the moment, but that there's some input-output function that a cell has, transforming its voltage into firing rates. Then you end up with an equation, tau, and then I make this a vector equation, and I'll use Byron's notation of a line under it for a vector. Then we have tau dv by dt is negative v plus w, or v plus w matrix now, times f of f vector of v, so the set of firing rates of all the neurons, plus an input vector. And that essentially is a rate model. We've gotten rid of spiking. Everything is expressed in terms of firing rates, which are assumed to be static functions of the voltage. You can, if you make a transformation that v is equal to w r, it's not the same r as this, but some other variable r, which has a relationship to this, plus, let me call it I for some other kind of input, then you can show that, that if all the taus are the same for all the cells, then this is equivalent to a rate model of the form dr by dt, tau dr by dt is negative r plus f of wr plus I, where the relationship between I and H is that I is a low-pass version of H. Tau di by dt is negative I plus H. And R turns out to be a low-pass version of this R. And so if all the taus are identical, these two models are equivalent. People tend to use either one when they talk about rate models without much rhyme or reason. They're if the taus are not identical, they're not equivalent, but I'm not aware of any significant differences in their behavior. And people just use them interchangeably. And I'm accustomed to writing things in this form, so I'm going to write things in this form, but we could do everything in that form, and all the results would be the same. Yeah?
What was the H story?
The feed forward, the outside of the network input into each neuron. External input. I sometimes call it feed forward, but I should say external. It might be top down. Yeah? Yeah, so if we define R by this equation, and that's not, let me call this a R twiddle or something. It's not quite the same. This turns out to be a low-pass version of that. But if we define R by this equation, then R satisfies this rate equation, which is the other form of the rate equation that people use. So typically we think of these R's as firing rates. They're actually a low-pass version of the firing rates if you start with the voltage equation as fundamental. But you know, this is also kind of a hack, so not necessarily any reason to count either one as fundamental. And I'll just say that there's an industry of trying to understand when you can legitimately derive rate models from spiking models, and usually it's in some kind of limit that doesn't really apply to the, like limit of slow synapses, for example. But in practice, if you study a rate model and then study a spiking model with the same connectivity but that's in a regime where the spiking is asynchronous and irregular, then the rate model gives you quite a good description of how the spiking model behaves. So it gives you quite a lot of insight. I can't prove that, but it's just a fact. And that's as much as I want to say about rate models. But they're so I'm going to be studying models of this form. Okay. So, but before we get into rate models, let me just talk a little bit about selectivity in visual cortex. So, you probably all know that, yeah?
Are you going to put the notes of this onto do you have this in written? Or?
No, I don't, but I will, I do have some problems. I'll give you problem sets which will develop some of the, it won't develop this really. Actually, if you want to know about this conversion, there's a paper, Miller and Fumarola, 2012, that derives this equivalence. Suppose you have some activity pattern. I'm just going to draw an activity pattern as a blob, as if it was a neuron, but I'm going to think of it as some pattern of activity across your neurons. If that pattern excites itself, it's going to turn up the gain of its response. So it's getting some input, but how much does it respond to that input? The more it excites itself, the more it's going to respond to that input. If it inhibits itself, it's going to turn down the gain. So one way to modulate gain is with loops, where a pattern of activity excites or inhibits itself, and so increases or decreases its response to the external input it's getting. The other way is that you have some input to one pattern which excites another pattern. And so the overall gain of your network's response to this input will be amplified by this, but in a different pattern than it comes in a way, a different pattern than the one it directly excites, but it'll still be amplified by this feed-forward connection. That can turn up the gain of your overall response to that input. And similarly, if that were negative, it could turn down, well, or it could give you a strong negative response, because this is linear. So, but basically, the feed-forward connection can modulate the gain of your response. And that's it. But so what does that correspond to mathematically? So you all have seen by now eigenvalues and eigenvectors, right? And how many of you don't feel completely comfortable with them yet? Anybody? Okay, a few people. What?
There should be at least 6 people that
Okay. So this picture is what's described by eigenvectors and eigenvalues. So the idea of eigenvectors and eigenvalues is you have some weight matrix. So I have my rate equation, tau dr by dt is negative r plus wr plus some external input. And you remember the eigenvectors are the vectors that just become a multiple of themselves under the matrix. And lambda I is the eigenvalue, ei is the eigenvector. And there's n of them if it's an n by n matrix. So what's an eigenvector? It's a pattern. It's typically related to the structure of your weights. So like if you have weights that, if you just had excitatory cells, I haven't gotten into inhibitory cells yet, just had excitatory cells, and the connectivity fell off with distance, then you would expect that the one with the highest eigenvalue would be all of the network active at once. The next one would be half the network active and half inactive, and there'd be two of those modes. And then the next one would be a higher harmonic and a higher harmonic. And so there's some, if you have some structure in your weights, I just want to get across, then the eigenvectors correspond to some corresponding structure of an activity pattern. They're not just some random things. And so what does this mean? This means that if we work in the basis of the eigenvector, so if we can express our rates, there's always almost always a complete basis of eigenvectors. In practice, there's always a complete basis of eigenvectors. So we can express this as what's the component, Ri as a number in the direction of the ith eigenvector. Then in that basis, so now the R's are the Ri's. They're not the firing rate of each neuron. They're the firing rate of each pattern, of each eigenvector. In that basis, W is diagonal. It's just lambda 1. The first guy is just multiplied by itself, lambda 2. The second guy is just multiplied by itself, lambda n, with all zeros on the sides. Okay, is that clear? Because that just means, W times R is you just take the first component and you multiply by lambda 1, you take the second component, multiply by lambda 2, but they don't talk to each other. That's what's special about eigenvectors.
And just when you have eigenvalues that are different than 0, you're not having a feed-forward network. So let's say the one on the left would work, but the one on the right, unless you
right. Yes, absolutely right. The eigenvalue picture describes this. It does not describe that. We're going to get to that in a minute. Okay, so and so what this is saying is this says that your activity patterns, your eigenvectors, are a set of loops where the first pattern is affecting itself with an eigenvalue with a effective weight lambda 1. Your second pattern is affecting itself with an effective weight lambda 2. Your nth pattern is affecting itself with an effective weight lambda n. And the lambdas might be complex numbers, and that's a little, but it doesn't fundamentally change the picture, that it's basically a weight, where if it has a positive real part, it's exciting itself, and if it has a negative real part, it's inhibiting itself. And so what the equation for one of these, this splits into a bunch of independent equations. Tau dr1 by dt is negative r1 plus lambda 1 r1 plus h1, and so on. The R1 equation doesn't involve R2 or R3 or R5, and the R2 equation, they each just only involve themselves. That's what makes it easy. It turns it into a bunch of one-dimensional equations. And we can solve this for the steady state, say. And so for the steady state, we set the time derivative to 0, and we find that R1 is equal to H1 over 1 minus lambda 1. So what does that tell us? Yeah.
The modes that you're drawing up there on the whiteboard, those are not necessarily neurons. Right?
Those are activity patterns. Those are the eigenvectors. Each one is a pattern of the whole set of neurons in your network.
Take the entire matrix to specify activity patterns
right.
of the neurons. So
right.
You're not talking about neurons anymore.
That's right. That's right. Is that clear to everybody? Got that? So we're talking about the pattern, an activity pattern that excites itself, or an activity pattern that inhibits itself, excites its own growth, inhibits its own growth. And we're talking about the input to that pattern, which you can work out mathematically is just, you can work out mathematically. You take your whole input vector and you break it up into what's the input to each pattern. So what does this tell us? It says that if lambda 1 has a real part that's bigger than 0, but, well, first of all, if lambda is bigger than 1, then this is minus 1 plus lambda, both multiplying R1. If lambda is bigger than 1, then this is equivalent to plus something times R1, plus lambda 1 minus 1 times R1. If that's bigger than 1, this is exponential growth, and we don't have a fixed point. But if lambda is less than 1, this is negative, that exponential decay to a fixed point. And then this will be the steady state. This will be the fixed point. So this is the steady state, but if lambda is bigger than 1, you're moving away from it, not towards it. Yeah?
Sorry, I was going to ask what happened with tau, but you multiplied by 0, so it's
That's right. That's right. So what this is saying, so if lambda is bigger than 1, your system's unstable linearly. And linearly, you can't say much more about it. But for the case lambda with real part less than 1, then it's saying if lambda is bigger than 0, I'm amplifying. In other words, if I have a positive connection, I'm amplifying. I get something less than 1 in the denominator, so I get something bigger than h1 for my steady state. On the other hand, if I'm inhibiting, if lambda is less than 0, then I get something bigger than 1 in the denominator, and I'm suppressing the response relative to h1. So you can see here the gain modulation from the loop. It's exactly in that term that you divide by 1 minus lambda 1 for the eigenvalue. OK, so why isn't that the whole story? Well, there's a problem when the eigenvectors are not orthogonal. And boy, I'm never going to get through this whole thing, but we'll get as far as we get. There's a problem when the eigenvectors are not orthogonal. And that is, suppose, let's just consider a two-dimensional system. And suppose I have two eigenvectors that are very close together in the direction that they point. And suppose I have an initial condition that points in this direction, and I want to express that as a sum over my eigenvectors. Well, I'm going to need to have a big component in that direction, a big component, positive component of this guy, and a big negative component of this guy that will add up to make this small component orthogonal to the direction that they're basically both pointing. And so I have two big things canceling to make something small in my initial condition. Well, you should think two big things canceling, that's not a stable situation. You change it around a little bit and suddenly you've got something big. They don't cancel anymore. And so suppose now this one is decaying faster than that one. This one has a more negative eigenvalue than that one, so it decays faster. Then after a little while, this one is decayed back to here, but this one's only decayed back to here, and your initial state has grown. And eventually, as time goes to infinity, this has to go back it has to come back to 0. But on any finite time, you can get arbitrary growth, basically. As one eigenvalue disappears and it was canceling another one, and suddenly that other one appears, and your pattern appears to grow, or pattern grows before it decays. And so this should disagree with your intuition that if both of these guys are decaying, you know, you're a sum of a bunch of components and all of them are decaying, then your rate vector should be decaying. But that's not true. You can get arbitrary transient growth before the steady state decay when the eigenvectors are not orthogonal. And so what that means is that although the eigenvector picture is an accurate description of the math, it gives you a very poor intuition. You would have an intuition, you know, if you were in the if I mapped the eigenvector basis as though it was orthogonal, you know, so here's my two eigenvector axes. I would start with a big positive component on one, a big negative component on the other, and I would think I was more or less decaying to 0. But back in my original space, I'm actually getting bigger and then getting smaller. So the eigenvector picture is very deceiving. So what do we do what's the simplest math we can come up with that doesn't distort the geometry of the actual path, that keeps the geometry of the actual path, keeps it getting bigger when it gets bigger and smaller when it gets smaller? Well, to do that, you start in some basis that you call orthogonal, the basis of your neurons, neuron 1, neuron 2, neuron 3. You want to rotate that, but keeping your bases orthogonal. You don't want to go to some basis like this. And so that's called a unitary transformation. It's a transformation where you maintain the orthogonality of your bases. And so what's the best, or it's called an orthogonal transformation if everything is real, but unitary more generally. So the simplest you can make your matrix with any kind of transformation is you can make it diagonal. The simplest you can make it with a unitary transformation is you can make it upper triagonal. You can make it where it has a set of feed-forward weights up here and a 0 down here, and it has the eigenvalues on the diagonal. And that's called the Schur transformation. And just like the eigenvector transformation, it's a transformation to a set of activity patterns. But now it's a transformation to a set of activity patterns that looks like this, where each pattern, or let's say pattern n, excites itself with lambda n but it also might excite pattern n-1 or pattern 1. Pattern n-1 excites itself with lambda n-1. Pattern 1 excites itself with lambda 1. But you also can have these feed-forward connections, but there's no loops between these patterns. It's only feed-forward because it's only in the upper trigonal. You can go from n to lower numbers, but you can't go from lower numbers back to higher numbers. That would require entries down here. And so in a basis that stays orthogonal, that's the best we can do is this layout, where we have both loops of patterns exciting themselves, and we have feed-forward connections between patterns. And just to try to make this complete, so when do you have orthogonal eigenvectors? You have that if and only if the weight matrix is what's called normal, where that doesn't mean as opposed to abnormal. That means like two things are normal to each other if they're orthogonal. That just means it's just a way of saying the eigenvectors are orthogonal. And it's normal when it commutes with its own transpose, or well, with its own adjoint if it's complex. But let's keep it real and let's just say with its own transpose. Now, what about biological weight matrices? Are they normal? Well, no, not if they have excitatory and inhibitory neurons. Because if you have excitatory and inhibitory neurons, let's say that we put all the excitatory neurons up top and all the inhibitory neurons on the bottom, then the weight matrix has to be all positive or zero entries for all the excitatory neurons, and it has to have all negative or zero entries for all the inhibitory neurons. And if you do the exercise of just take that structure I'm not going to try to do it on the board, but if you do the exercise of take that structure and multiply it by its transpose and reverse the order, you don't get the same thing. So just having that structure ensures that it's non-normal. And let me take you through a very simple case that you can do on the board fairly easily. And for the aficionados, the way you do the Schur transformation is you go to the eigenvector basis. You order your eigenvectors in some arbitrary order. So the Schur transformation is not unique. It depends on how you order the eigenvectors. And then you do Gram-Schmidt orthogonalization and to create an orthogonal basis from the eigenvectors. And the result will be in that basis that you have this structure for your matrix. So the feed-forward weights are, the eigenvalues are always the same eigenvalues. The feed-forward weights vary depending on which Schur basis you use. But what is conserved about them is under a unitary transformation, the sum of the absolute squares of all your weights is conserved, of all your matrix entries is conserved. So since the eigenvalues stay the same, that means the sum of the squares of all the feed-forward weights is a conserved quantity. So there's some overall sense of how strong is the feed-forward connectivity that's conserved. It doesn't matter which Schur transformation you use. So let's take a simple case of a 2x2 matrix where we just have the same weight for the excitatory connection to the excitatory cells and to the inhibitory cells. Consider the case where we just have an excitatory population and an inhibitory population, and they have some connections between them. But we're insisting that both of the I connections are identical, and we call them negative WI just so that the W is positive, and we put the negative sign in by hand. And both of the excitatory connections are identical. So we can find the eigenvectors of this, and I'll just tell you what they are. One of them is WI, WE, and that has an eigenvalue of 0. And the other is 1, 1, and that has an eigenvalue of WE minus WI. And it's easy to verify if you multiply that that's what you get. So So now let's build our Schur basis. And let's take this as our first Schur vector. And the second Schur vector has to be orthogonal to this. So that can only be something proportional to 1 minus 1. That's the vector that's orthogonal to this in 2 dimensions. So in 2 dimensions, once you've picked your first vector, you know what your second vector has to be. So what does this matrix look like in this basis? Well, when W acts on, so here, let me erase this diagram. And so when W acts on 1, 1, right? Well, we already know that that gives, let's call this lambda 1. And let's call this lambda 2, 0. So W acts on this, we get WE minus WI times 1, 1. And I haven't, actually, the eigenvectors should be normalized so that you should multiply them by 1 over square root of 2 to make them have length 1, but I haven't bothered to normalize them. Just saying what direction they point in. When I multiply by 1 minus 1, what do I get? I get WE plus WI, WE plus WI, which is WE plus WI times 1, 1. So I've multiplied by the second vector, and I got something proportional to the first vector. And that amounts, so now if I want to express the matrix in this basis, then I have W1 acting on itself, or sorry, W acting on 1, 1 has an eigenvalue WE minus WI. W acting on, and it doesn't do anything, it doesn't give me anything in the W2 direction. Right, so I get a 0 here. And W acting on the second vector gives me WE plus WI times my first vector. And it doesn't give me any of my second vector back, so I get another 0 here. So here's my 2 eigenvalues, this one and this one. So let's call this lambda 1, lambda 2, 0, and W feed forward. And so we see W feed forward is the sum of the 2 weights. The eigenvalue is the difference of the 2 weights and plus 0. And what this means basically is, suppose, so I have this pattern where the 1, 1 vector, let's call this this is the sum, because this represents equal activity of E and I. Let's call this the difference, because this represents E going up when I goes down, or E going down when I goes up. So I have the difference, doesn't have any connection to itself, has eigenvalue 0, gets some input to the difference, and then it's connecting with W feed forward to the sum, which is connecting to itself with lambda 1, which is the difference of these two. And so what you can see in this case is that if lambda 1 is small, that is, if E and I are fairly balanced, but they're big, then I get a big feed forward weight, and almost my whole recurrence starts to be just the feed forward weight. You know, if they were completely balanced, so lambda 1 was also 0, then all my recurrent effects would be described just by this feed forward weight. And so there's 2 things going on. One is I get an eigenvalue where E and I drives itself according to how excitation dominated or inhibition dominated the connectivity is. If it's excitation dominated, the sum excites itself. If it's inhibition dominated, the sum inhibits itself. And then I get a feed forward weight, which doesn't care if E or I is dominant, just cares how big my overall weights are. If I make my weights big, then I get a big feed forward weight, and that starts to become the dominant effect. And so how does this give you gain modulation? Well, it's a linear model, so it isn't quite gain, but it gives you a change in activity as follows. If I if I give an input that is weighted toward the I cells, then I'm giving an input that is negative toward the difference, right? Right, because I'm giving positive input to a -1, so it's a negative input. So I weight this, so if I'm giving input to I cells, then I'm giving input to this guy that is negative. I'm also giving input to this guy that's positive. And so, but now I give a big, so the feed forward, because this is the, way I give input to the inhibitory cells, that's also an input to this pattern. But so the fact that I'm giving input to the inhibitory cells, that's positive input here, is driving the sum up. But the fact that it's driving the difference down, and the difference is driving the sum with the feed-forward weight, is driving the sum down. And so you have these two competing effects. You have the normal effect, or the eigenvalue effect, which is just the feed-forward effect plus whatever the eigenvalue is doing. But you also have the non-normal effect, which is going in the opposite direction. And so what this means is I can get a paradoxical effect, where if this weight is big enough, I can add input to my inhibitory cells and drive both E and I down. And so paradoxically, I've added input to my inhibitory cells, and in the new steady state, the inhibition has lowered its firing rate because of this non-normal effect, because I'm driving down the difference, and that's driving down the sum. And that's combating the direct excitation of the sum. Yeah?
Sorry, could you just give an input, just write down an input to both sum and difference, because I didn't quite get that.
Yeah, so what I'm saying is, suppose my input in my original basis, in my EI basis, my input was 0, 1. I'm just giving input to the inhibitory cells. Then in the sum component of that would be, because this is an orthogonal basis, I can just take the dot product to say what's its component in each direction. So the dot product with this guy, this should have a 1 over square root of 2 in front of it, but so the dot product with this guy would be 1 times 1 over square root of 2. And the dot product with this guy would be minus 1 over square root of 2. So this becomes, in terms of the sum and difference, in this basis, so in this basis my input vector looks like this. In this basis, the vector looks like 1 over square root of 2 times 1 minus 1. I'm giving positive input to the sum and negative input to the difference, because I just take the dot product of each of these vectors with my input to figure out what's the component of this guy in this direction, what's the component of this guy in this direction. And so that's why this is a negative input and this is a positive input. And so they're having opposing effects on the sum. Who's still confused? I probably haven't been very clear.
So again, how do you come from the EI input to the sum difference?
Okay, so here I'm expressing the sum and the difference in the original basis, right? This is in the EI basis. This is what they look like in the EI basis. This is what my input looks like in the EI basis. So to know what its component is in this direction, I just take the dot product with this vector. To know what the component is in this direction, I just take the dot product with this vector. I can take the dot product in any basis I want. I can take it in the original EI basis. Dot product doesn't care what basis you're in.
One more question. Is that how you usually get those?
Or it doesn't care what basis you're in if you make a unitary transformation. If you preserve if you keep everything orthogonal, so you preserve distances, then the dot product doesn't care. Yeah.
Is that how you usually get those? I don't know what you call it, motors or whatever. Is that only a basis transformation in any cases? I mean,
yeah, it always is a transformation to a different basis. You start out in the basis of your, one vector is just this neuron active and all the other ones silent. The next basis vector is this one active. In other words, you start out in the single neuron basis, and you go to an activity pattern basis where there's some pattern of activity across all your neurons, like E and I both active, or E going up while I goes down. So you're going from the original basis of just one neuron active at a time to pattern basis.
So the choice of the other basis really depends on what you want to work with, right?
Well, it depends on the weight matrix, because remember we're considering these special bases. One is the eigenvector basis, and that's unique, and that's where the matrix is diagonal and it looks just like loops. Just each activity pattern talks to itself and doesn't talk to anybody else. But the problem with that is you lose, your pattern of E and I activities can be getting bigger, and you would think in that basis they were all getting smaller. So if you want to keep the geometry and know when things are getting bigger and when they're getting smaller, you want to do go to an orthogonal basis of patterns. And that gives you this structure with the feed-forward connections. But it still isn't just an arbitrary, there's a number of Schur transformations that depends on how you order your eigenvectors before you orthogonalize them. But there's not just any old Schur vector. I mean, there are still a special set of basis vectors that give you this structure of the weight matrix. So you notice, I mean, in this case, I started with one of the eigenvectors. If I hadn't started with one of the eigenvectors, I wouldn't have gotten this special structure with a 0 over here. So what this is saying basically is if my feed-forward, so the generalization, and I haven't proved this to you, I just showed you a very special case, but you consider a general n-dimensional matrix with excitatory and inhibitory cells, and very commonly, I can't really prove it, but very generally what you seem to find is that if your weights are strong, but E and I are relatively balanced, or inhibition is dominant, that if inhibition is dominant, you get negative eigenvalues. If they're relatively balanced, you get fairly weak eigenvalues. But because your weights are strong, you get strong feed-forward weights. And you get these strong, and the feed-forward weights tend to be from patterns that involve E and I changing in opposite ways, differential kinds of patterns, to patterns that involve E and I going up and down together, some patterns. And so the way to think about it, it's not a proof, there's probably exceptions, but the way to think about it is that if you give input that tilts the balance toward the inhibitory cells, you pull down both your E and your I activity, if your feed-forward weights are dominating your eigenvalues at least, or dominating the feed-forward input. Dominating the external input. If your feed-forward within the network weights are dominating your external input, then if you give input to the I that tilts the balance towards I, a little bit of, tilt the difference towards I, you tend to drive both E and I down. You tilt the balance towards E, you tend to drive both E and I up. And because there's a linear model, that's just an additive. You just add that to whatever response you were getting to some other inputs. But in a nonlinear model, it often tends to be scaling. It tends to be a multiplicative gain change, where you're pushing both the E and the I up, or you're pushing both the E and the I down. You're changing the gain of your whole network. And so I think that's as much as I'm going to say about the non-normal matrices, that these effective feed-forward weights, and you'll have a problem set that'll get you through more details of it and give you hopefully a better grasp of it. I do want to say a little bit more about this paradoxical effect, that you give input to the inhibition and you drive down the inhibitory cells in their new steady state. This was an effect that, without thinking about non-normal matrices, but this was an effect that Misha Sodix discovered in a 1997 paper in a model of the hippocampus. And we rediscovered it and then found Misha's paper when we were thinking about a result of David Furster on surround suppression. And so the result was, he considered, do you want to take pics? So he was studying surround suppression. So he would take a cell and he would give it an optimal drifting grating stimulus, optimal size. And then he would also consider a very big stimulus of the same, everything else the same, orientation and so forth, that would cause a suppressed response. And everyone had assumed that when you give the big stimulus, you're exciting adjacent regions of cortex that are millimeters away. And the only connections into the local piece of cortex where you're recording, where your cell is, are long-range excitatory projections, because inhibitory cells don't make long-range projections. And since you're driving the firing rate down, everybody assumed, oh, well, you must be preferentially targeting the inhibitory cells. You're driving up the rate of your inhibitory cells, and that's driving down the rate of the cells you're recording from. And so the picture was that the inhibitory cells are not surround suppressed, because they're going up in order to inhibit everybody else and make everybody else surround suppressed. And so the picture was that if you record from a cell that's being surround suppressed, you should see it's being suppressed because the inhibition it receives goes up. And so David did the intracellular recordings, or David's lab did the intracellular recordings. Hirofumi Ozeki did the intracellular recordings and found that to a small stimulus, you got, or let's say, right, so if you looked at the inhibition that the cell received for a small stimulus and the inhibition that the cell received for a large stimulus that was suppressing it, that it tended to receive either the same or more inhibition for the smaller stimulus than for the larger stimulus. It was actually, the inhibition was going down when it was surround suppressed. Well, how could that be? Well, our interpretation was that the inhibition is also being surround suppressed. E and I are all being surround suppressed. Well, how could that happen? Well, that's this paradoxical effect, that you're driving excitation into the local region that's biased towards inhibition, and the net effect is to drive both E and I firing rates down. And so, since the I firing rates are down, you're receiving less excitation, less inhibition, and it's really a de-amplification. We call this balanced amplification, this turning up and down of the gain of the whole network based on tilting the difference between E and I. And so you had a certain amount of balanced amplification. The surround input comes in and turns that balanced amplification down. And both the E and the I go down. And so one thing that this gives you is kind of a knob on amplification. That is, if you put in an external input that's biased towards I, you de-amplify everybody. That's what surround suppression seems to be. If you give an input that's tilted towards E, you amplify everybody. And so you can turn up and down this amplification with, for example, surround suppression. And we actually think attention may be doing the same thing, but turning up the gain by giving some input that's biased towards E cells. But we don't have any proof of that. Let me just give you one more intuition for how this paradoxical result works, and then we will move on and race through the last part. And that is, so although I've given you a linear account of this paradoxical effect, it also survives in a nonlinear model, and you'll do that with null lines in an exercise, and you'll see the same effect in a nonlinear model. But let me just give you the intuition, and the intuition is as follows. So you have an E population and an I population, and they're connected, and you have some external input, let's say your center stimulus, and you're at some fixed point for your external input. And now, so there's some firing rates driven by by this center input. And now you add the surround, and for simplicity, let's think of the surround as just targeting the I cells, although it actually targets both. So you're adding some input to the I cells. So what happens? Well, initially the I cell raises its firing rate, and that lowers the firing rate of the E cells. And now there's a critical distinction we have to make between whether the excitatory subnetwork was stable by itself or would have been unstable but is being stabilized by the inhibition. So what do we mean by that? We mean consider the center-only fixed point. So let's forget about the surround input for a minute. Consider the center-only fixed point. And if I was to freeze the inhibitory firing rate and not let the inhibition dynamically respond, then if I tick the E firing rate up a little bit, if it's unstable by itself, it means it recruits too much recurrent excitation, so much that it wants to keep going up. And if I tick the E cells down a little bit, it means it loses too much recurrent excitation, so much that it wants to keep going down. Then the E would be unstable by itself. It's like a pencil balance that you tick it and it wants to keep going in the direction you ticked it. But the network can be stabilized by the fact that by the feedback inhibition, the fact that if this starts going up, it pulls the I up with it, and that pulls the whole network back down. And vice versa. If this starts going down, it pulls the I down with it, that pulls the whole network back up. So precisely so it turns out the condition for, and you'll prove this in at least one case in your problem set, the condition for this effect to be bigger than that effect, the condition to get the paradoxical effect is precisely that the excitatory subnetwork be unstable by itself. If it's unstable by itself, then so now you've added this surround input, the I firing has gone up, the E firing has come down, then it's lost too much recurrent excitation to support that lower firing rate. And not only that, but it's got more inhibition than it did when it started, when it was at the center-driven fixed point. So it's got too little recurrence, it's got more inhibition, So it's just in free fall. It's going down. There's nothing to stabilize it. And it keeps going down until it withdraws more inhibition, more excitation from this inhibitory cell than you added to start the process. Sorry, so you're, right, so this is going down. And now your inhibitory cell is receiving less excitation than it was initially. And so now it goes down below its initial firing rate at the center-only fixed point because it's receiving less excitation. And now you'd say, well, now this guy's receiving less inhibition than it did at the center-only fixed point, so it ought to go up and we ought to oscillate. But no, because remember, when it went down, it lost too much recurrence to support that lower firing rate. The only way to stabilize that lower firing rate, given that it lost too much recurrent excitation, is it's got to be getting less inhibition to compensate for the over-strong loss of recurrent excitation. So now it's getting less inhibition, and that's your new stable state. Both E and I have gone down. And that's the paradoxical effect. You add input, and the I cell goes down in the new steady state. And so that's what we think is happening in surround suppression. And the smoking gun was the prediction that if you could do the time-resolved conductance measurements, you would find that the inhibition in your surround suppressed cell went up transiently before it went down in the steady state. And so Hirofumi Ozeki and David Furster went back. They spent a year doing the time-resolved conductance measurements, and indeed they saw the inhibition went up before it went down, but in the steady state it went down. So we think that's what's happening. Okay, so that's what we call the ISN, the inhibition stabilized network. And let's see, this language, Hebbian amplification, I think of as that's the loops. That's the pattern exciting itself, because Hebb talked about recurrent assemblies where patterns excite themselves. So we call the loop Hebbian amplification. The feed-forward weights we call balanced amplification, because if you have a balance of E and I, but they're both big, then you get these big feed-forward weights from differences to sums. And then the ISN is the inhibition stabilized network. Precisely when your network's inhibition stabilized, you get this paradoxical effect of inhibition going down when you try to drive it. Yeah?
Is this at all similar to liquid state computing and liquid state machines, or not really?
Not really. This is all about fixed points. And liquid state computing is where you don't have a fixed point, where you're just traveling along.
You have one.
Yeah?
Point at 0.
Okay.
The system has to be stable, otherwise.
Okay, but the interest is in all this transient dynamics and not in fixed points. I mean, I guess if you had a linear model, then this non-normal dynamics might describe some of that transient dynamics, but typically they're not thinking about linear models, I don't think. Okay, so I can go to 130? Okay. So I mentioned to you that a rate model, for it to be a good description, you need to be in an asynchronous and irregularly firing regime. So when are you in an irregular firing regime? By irregular firing, we mean you fire more like a Poisson process than like a clock. Your spikes come at irregular intervals, even if you're getting a steady input. And that's the regime we think Cortex is in. And there's a simple, at one level, there's a simple answer to that. And that is, if this is your voltage, this is time, and this is your threshold voltage, and let's say you start out at some reset or rest down here, and let's say you're given some constant input. Well, if that constant input drives you to your mean input is driving you up to a mean voltage that's way north of threshold, then you're going to be integrating toward that. You're going to hit threshold and fire. You're going to be integrating toward that. You're going to hit threshold and fire. And you're going to fire in a very clock-like way, because it's going to take you roughly the same amount of time to get that far towards what you're integrating toward every time. So if you're firing on the mean, if the mean is what's driving you up to threshold, then you're going to be firing very regularly. On the other hand, if your mean is subthreshold, or even perithreshold, well, you're going to have some refractory period during which you're basically integrating up to your mean, but then you're going to fire, it's going to be fluctuations that drive you to fire. You'll be driving on fluctuations, not the mean. You'll be fluctuating about this mean here. And a fluctuation is equally likely to come at any time as any other time. So firing on the fluctuations means you're a Poisson process. You're equally likely to fire at any time. So other than having, if you're firing on the fluctuations, in this simple picture, you're like a Poisson process with a refractory period. And you're firing very irregularly. And now there's other reasons why you could fire irregularly. You could have very correlated inputs. So your inputs arrive all at once every so often, and they do it as a random Poisson process, then you'll fire every so often as a random process. So this is sort of in a picture where we're thinking of having uncorrelated inputs. But why would you fire randomly anyways? And it's because you're firing on fluctuations. You can have correlated inputs. There can be stochasticity in the synapses and in the cells, in the channels. And that can contribute to irregularity. And indeed, there was a paper from what is his name in Israel? There's these two Israelis whose last names are interfering in my mind right now. It's not Seidemann, not Eyal Seidemann, but it's the other one that sounds like that, who is the theorist. Sorry, apologies to you, whose name I'm forgetting right now. Anyways, he worked with Idan Segev, the first PhD. He's now a theorist doing his own work in Israel. And they showed that there were so few, at the point where the Hodgkin-Huxley neuron, the sodium channels take off, there are actually so few sodium channels activated that it's very stochastic when you get to threshold. And they were saying, therefore, that just from the stochasticity of the sodium channels, you could account for a lot of irregularity of firing. There's other factors that can contribute to irregularity. We're going to ignore those, and we're going to assume the theorist picture of you have uncorrelated inputs and your stochasticity, and these other factors are not the main thing that's making you irregular. Then to the theorist, many theorists, the main thing that's making you irregular is that you're firing on the fluctuations. Certainly, that's one thing that can make you irregular. So what leads you to fire on the fluctuations? Well, so your mean input better be subthreshold. That means that somehow your inhibition has got, either your excitation has to be very weak, or else your inhibition has somehow got to cancel enough of your excitation that the residual is subthreshold. So you have to have some kind of balance between the excitation and the inhibition. So how do you get a balance? And there were a bunch of people who started to work on this. Misha Sodiks had a very seminal paper. But the paper that became the dominant model was from Van Vrieswijk and Sampolinsky, where they showed that with some very simple conditions, a network will reach a balanced fixed point where the excitation and the inhibition are largely canceling, leaving a small residual. And it'll just dynamically go there. So it provided some overall conditions on the weight matrix are satisfied. You don't have to fine-tune it. That's just the fixed point solution, is a balanced solution. And what that looks like very briefly, and I'm leaving a lot out, is so they have some mean field equation. They had some model of binary neurons that were spiking-like neurons. And you end up with some mean field equations for the net, and they had random connectivity. So you have the net excitation, the net inhibition, and just mean field equations for the excitatory and the inhibitory firing rates. And so R is just the excitatory firing rates and the inhibitory firing rates. And their mean field equations, the steady state was that the R vector was just some function of a 2x2 weight matrix, effective weight matrix times the rate plus the feed-forward input. And this function was such that, order 1, it was saturating at 1 and -1, and the range of saturation was maybe plus or minus 3. So basically, inputs of size 1 give you outputs of size 1 through this F function. And the assumption they made were the following: that you have a given let's think of how many excitatory inputs does a cortical cell get. That a given cell gets K inputs, which they thought of as a large number, like 10,000, of strength J, like half a millivolt. And in an integration time, tau, if tau is the integration time of your membrane, then it fires it receives R tau spikes, where R is the average firing rate of each of your inputs. It receives R tau spikes in time tau, from every one of your inputs. And so your mean input would be k, j, r tau. Now the variance in your input, if you assume that it's asynchronous and irregular and firing as a Poisson process, and then you see self-consistently does that turn out to be true. If it's firing as a Poisson process, then the variance will be r tau, the variance in the firing of each neuron, of how many spikes you get. The count variance is equal to the count mean for a Poisson process. But the variance will have a factor of j squared, and then all of your inputs are independent, so the variances that just add, so you get a factor of k. And so you get sigma squared is k j squared r tau. Or in other words, we can say that sigma is j times square root of k r tau. Whereas this guy we can write as j times k r tau. And so the sigma over the mean is 1 over square root of k r tau. And so, but they were thinking of k as a very big number, so big that k r tau was a big number. And if k r tau is a big number, then you have a problem, which is if you make what you want to be firing on the fluctuation. So if you consider the distance from rest to threshold to be 1, let's just work in voltage units where that's 1. So then you want your mean to be order 1. You want it to be somewhere down here. You want your fluctuations to be order 1, because if they're tiny, then you'll never spike. You won't have any kind of firing rate. So you want both of these to be order 1, but if this ratio is tiny, you can't do that in any obvious way. If you set your j to be 1 over k, then your mean is order 1, but your sigma will be order 1 over root k. It'll be tiny if k is a big number. So they just think of k as this big number, and they're trying to say how do things scale with k. And on the other hand, if you set j proportional to square root of 1 over square root of k, then the mean is order square root of k. It's too big, but sigma is order 1. And then they went, aha, but this big mean can cancel because E and I can dynamically cancel and balance and give us a mean that's order 1. And the way that works is basically, so you think that your net weights are, the mean input coming into E cells is order square root of, so they're going to choose this scaling. And so your mean input is order square root of, your mean weights are order square root of k. And they also have to assume the feed forward input is equally big. And then what you find is if you set r as some r0, which is order 1, then how do we make this self-consistent? Well, so we have an r0, which is order 1 over here. But here we have 2 square root of k quantities. And so to end up with something order 1 in here, which is what we want for we don't want our mean to be pinned up against the top. To end up with something order 1 here, these 2 square root of k quantities must cancel. So you have to have that WR0 is equal to negative h. And that's the balance equation. That says that the first order term in the rates exactly cancels the external input to leave us with complete cancellation, no net input. But now you need an additional term in the rates to leave something order 1 in here, so I have some finite input. And what does that have to be? Well, that has to be something over square root of k, which gets multiplied by square root of k, and leave something order 1 in here. And then you would go on, ... higher order terms in 1 over square root of k. And so you can sort of see that you could build a solution like this, where you end up with something order 1 in here, and order 1 over here, and everything's self-consistent. And they were able to show that with simple conditions on this 2 by 2 W matrix, that the determinant of W was greater than 0, and a couple of other conditions that I'm not going to go into, that you could guarantee that this was the fixed point and this was the only fixed point. So the network would dynamically go to this balanced state, and it was a stable fixed point. So that's the balanced network, and it solved the problem of dynamically, without any fine tuning, how is it that you're firing on the fluctuations? How is it that you're getting irregular firing? It has a couple of problems. One is that because they're assuming k is a very big number, this is negligibly small compared to that part of the rate. But that part of the rate is linear in the inputs. R0 is negative W inverse times the feed-forward input. So this model can only give you responses that are linear in the inputs. You can't get any of the nonlinearities that we see in Cortex. Now, you might, Tatiana Chumachenko, who will be talking tomorrow, has shown that you can get some nonlinearities in the balanced network if you put in synaptic nonlinearities, like synaptic depression and facilitation. But whether you get the right kind of nonlinearities to explain Cortex is an open question. We don't know. So it's not, completely out for that reason. The other problem with the balanced network on its face, I mean, it solved a big problem, which was, how do you dynamically get into this regime? The other problem with the balanced network is that it says that you have a tight balance, that the things that are canceling are much bigger than the residual that's left, right? The things that are canceling are order square root of k, and the residual that's left is order 1, and k is some big number. So that means if I was to silence Cortex and just reveal the feed-forward input, I should see it's huge compared to what I had with Cortex intact. And David Furster and Massimo Scanziani and Li Zhang and whatever her name is, Tao, have silenced Cortex in cats and in mice. And what's left is comparable to what was there with the Cortex intact. It's not orders of magnitude bigger. In fact, David Furster finds it to be smaller, that he gets about a third to a half as much voltage with the Cortex gone as with the Cortex present. So, and you can also go through some numerology, which I won't do here, but if you do the numbers on this, it turns out that this number is maybe somewhere between 1 and 1/10. It's not some horribly small number. And in fact, the sigma is about, I don't know, 1/10 to 1/4 of the mean in terms of the voltage sigma and the voltage mean. So the numbers don't really suggest you're in this regime of very huge things canceling to leave something small. And you notice that if it's not very huge, then this second order term would not be negligible compared to the first term. But the second order term is not linear in the input, and that leaves a lot of room for nonlinearities and nonlinear response properties. So if you have a loose balance, maybe then that could be compatible with the fact that the things that cancel are comparable to what's left, and that you have very nonlinear behavior in Cortex. So in the last 10 minutes, I will tell you.
What does that say about balanced amplification, what you have on the right side of the plate?
Okay, so balanced amplification is a linear mechanism, and it will turn out, it's, in a nonlinear model, I mean, like when you study thinking about the linear mechanisms, like the pattern, like eigenvalues, patterns that excite themselves, and like feed-forward connection still is insightful. Particularly, you can linearize about a fixed point, and you get a lot of insight from the linear dynamics. But we're now talking about nonlinear models. And so a lot of this balanced amplification and Hebbian amplification is there under the hood in the nonlinear models, and particularly if you're linearizing about a fixed point, it's very easy to see. But it's now in a nonlinear context where it may not be the...
And then in the context of having tight versus loose balance in real systems, like can you get balance amplification in systems that are tight versus that are loose?
Yeah, in the tight balance, the other thing that happens in the tight balance is that all your eigenvalues become very large and negative. I mean, probably order square root of k. I'm not quite sure, but I think they're very large and negative, which means your dynamics is incredibly fast, which means there's no time for... this is something I didn't talk about with the non-normal dynamics. One of the key things, let me come back, take a step and come back. One of the key things that differentiates the non-normal dynamics from the Hebbian dynamics is that the loop amplifies by slowing you down, slows your dynamics equally to how much it amplifies you. Whereas the feed-forward weight allows you amplification without any slowing. And in fact, if the associated eigenvalues are negative, you can have a situation where, without the recurrence, you would have a growth to some steady state. With the recurrence, you have a very amplified growth to steady state, but it can be even faster than without the recurrence. So we have this idea that the recurrent effects come in late. That's not true, because with negative eigenvalues, that can speed up the dynamics, and the feed-forward weights don't slow the dynamics very much, and the net effect can be a speeded up dynamics, which is amplified by the recurrence. So that was one of the other things we really liked about the non-normal dynamics, was that it gave us amplification without slowing down, whereas the loop amplification equals the degree of slowing. So now, in the balanced network, you tend to get, about the fixed point, you have very large negative eigenvalues. And so your dynamics is sort of slammed shut. It slams to the fixed point. And that pretty much prevents, basically if the eigenvalues and the feed-forward weights both contribute to whether you're amplified or de-amplified. If the eigenvalues are huge and negative, it basically kills any amplification. But with loose balance, they don't have to be huge, and you can have all these effects. So I'm not going to be able to say very much about our model, which we call the SSN, the Stabilized Superlinear Network. Oh, sorry. So I'll say, when you get these pictures, the one about the Priebe and Hansel part, please don't distribute that picture. I don't want to mess those guys up. So I will just sketch, you can read about it, but we have what we call the stabilized superlinear network. The basic idea is that f function that f function is a power law. So that you rectify this element by element, and then you raise it to some power n, where n is something on the order of 2 to 5. So if this is your input and this is your rate, it looks like that. And there's no saturation. Now, we know that real neurons saturate, but when people record intracellularly and they look at the voltage here, which we can use perhaps as a surrogate for the input, in 30 millisecond bins versus the firing rate in 30 millisecond bins. Nick Priebe and David Furster did this. It's very noisy, but if you average it, it's very well fit by a power law. Look at the average rate for a given voltage in each voltage bin. And you expect this power law in a spiking model when it's firing on the fluctuations and not on the mean. So you can, if you take a integrate and fire model with white noise, and you look at its firing rate versus its mean input, and it has this shape while it's firing on the fluctuations, and you can fit that very well with a power law. So what does this do for you? The basic intuition is that your response for a given change in input is monotonically increasing. When I was going to say, you see this over the full dynamic range of visual stimuli that you show a cat V1 cell. So although we know the cell has to saturate, you don't see that saturation over the full dynamic range of where visual cortex is operating, at least in the anesthetized cat. So that's why we're going to ignore the saturation. And so long as you're in this superlinear regime, that's why we call it the stabilized superlinear network, you have a superlinear input-output function, then your gain is growing as the network activation, as the cell's activation is growing, as the network activation is growing. So if you think about what's the effective connection between two neurons, or it's basically when I jiggle this one's rate, how much does this one's rate jiggle in response? And that's the product of two terms. It's the actual synaptic strength, how much current do I inject, times the gain of the postsynaptic cell. For the given current, how much does the rate fluctuate? And this is exactly what you get if you linearized about a fixed point. That's what you would get for the effective weights of your linearized model. So what does that do to have your weights, your effective weights increasing? Essentially, when the gain is very weak, when the weights are very weak, then so all of you have external synapses and you have your recurrent synapses. Now these are neurons, not patterns. You have your external synapses. So the external synapses are weak. Your neurons are not very sensitive to them. Your recurrent synapses are weak. Your neurons are not very sensitive to them. But if you're in, if your parameters are such, and you can, Tatiana actually has worked out, you can guarantee conditions when this will be true. If your parameters are such that when your input goes to, your external input goes to 0, that your firing rates go to 0, your network doesn't have a high state where it's active without input, then any recurrent drive involves 2 or more of these weak synapses, because you need an external synapse to drive cortical activity, which drives the recurrent synapse. And just like x squared is always, much smaller than x when x is small, any recurrent effects involving 2 or more of these weak synapses become very small compared to the feed-forward synapses, feed-forward effects. So for the weak activation, weak external input, then you become very weakly coupled. And you're basically just driven by your feed-forward input. But now, and because so your net input is just the sum of the feed. If you give 2 different stimuli, your net input is just the sum of the feed-forward inputs for those 2 different stimuli, and it goes through a superlinear input-output function. So you get superlinear summation. You get more than the sum of the responses to the 2 stimuli. But now, when you have strong coupling, or strong feed-forward input, you become strongly coupled. X squared is much greater than x when x becomes big. So you become recurrently dominated. The recurrent input is the dominant input. And it turns out, and this is the connection to the balanced network, it turns out that in order to stay stable against this is sort of like a very explosive nonlinearity, and that if you start, as the recurrence gets stronger, and you reach the point where the excitatory subnetwork by itself would become unstable. If you had a fluctuation of the E cells, it would recruit so much recurrence that it would fluctuate even higher. But if you're in a regime which you can define in terms of the weight matrix where the inhibition keeps you stable, where your inhibition stabilized, so you become an inhibition stabilized network, and it turns out that in order to stay stable against this explosive nonlinearity, where if you start to go unstable, your effective weights would get even stronger, the network has to balance, has to conspire to balance. You have to have your firing rates are given by some expansion that looks like this, an R0, which is order 1, and then which cancels the feed-forward input. WR0 is negative H. And then a next order term, which is basically the magnitude of your input over some typical magnitude of your recurrent weights times an R1, which is order 1, and then you have a parameter alpha to the negative 1 over n, where alpha is the dimensionless parameter that controls the behavior, and alpha is just the norm of your feed-forward input raised to the n minus 1 times the norm of your recurrent input. So it's a measure of how strong your input is. And so the next order term grows as alpha to the negative 1 over n, and then you get lower order terms in alpha. But the key thing is that the transition between these 2 regimes happens for alpha order 1. And for alpha order 1, this term, if your feed-forward input and your recurrence are the same order of magnitude, then this term is comparable in size to this term. And actually, this term is also, I should say, this term is also proportional to that, so it doesn't depend on that. They're all proportional to this I over W. But then, there's these terms. So this term is comparable to that term. So you're in a loosely balanced regime where what's left over is comparable to what's canceled, and where you can have the nonlinear behavior. And it turns out, in this regime, basically, this is hand waving, but because of this balancing, when I add 2 different feed-forward inputs, most of the extra feed-forward input, or 2 different stimuli, most of the extra feed-forward input from the second stimulus is canceled by the balancing. And the result is I get sublinear summation. And that's hand wavy, but you very robustly get sublinear summation in this regime. Your response as a function of how strong your input is can become either linear or sublinear, depending on parameter regime. But when you add two different stimuli, they almost always add sublinearly. And so you get this sublinear summation that becomes linear around the transition and then even becomes superlinear. And you get all the phenomena I told you before in terms of surround suppression that depends on contrast, adding two stimuli that depends on contrast. Another characteristic of this regime is that the harder you drive the network, basically at the transition where you're just going unstable and getting stabilized by inhibition, you're as close to instability as you're going to be. And as you drive it harder, your eigenvalues your leading eigenvalues, which were as close to 0 as they were going to be, or as close to +1 for the weight matrix, start moving more negative. And so because your eigenvalues are moving more negative, those modes, their fluctuations are being damped. And the effect is that the shared variability in your network, the harder you drive your network, the more the shared variability is being damped, which is an effect you see across all kinds of systems, that as you drive the network harder, shared variability gets damped. So there's a whole lot of, and another effect is that because the harder you drive it, the inhibition has to grow faster than the excitation to stay stable. So if you look at the ratio of the excitation to the inhibition that a cell receives, that decreases the harder you drive the network. And that's been seen now both by Dan Feldman in somatosensory cortex and by Hilal Adesnik in a paper that's accepted, so I can talk about it, that's about to come out in Neuron, where he sees both with increasing the size of a stimulus or increasing the contrast of a stimulus that the E to I ratio goes down, as this predicts. So this accounts for an awful lot of data, and it fits, it keeps you in this irregular regime, and it fits with the idea that you have nonlinear behavior, it gives you the right nonlinear behaviors, and that you have components that cancel that are comparable to the net. So there's at least one believer in the world in this model. Maybe the rest of the world will convert eventually, but maybe not. And you can read a lot more about the model. And that's it. Thanks.